We have a chandelier. The chandelier has a mass of 40 kilograms. It's attached to the ceiling of a large concert hall by 2 cables. Now these cables don't go straight up because there's fancy decorations at the top of the ceiling, so they couldn't just anchor it straight up to the wall. So what they did is they took the chandelier. Here's my fancy chandelier. They used 2 cables. One of the cables, cable 1, makes an angle of 20 degrees with the ceiling. And it has a tension of 300 newtons. So that's one of our cables. The second cable comes over here somewhere. The question is how much tension is there and what angle does it make with the ceiling? So we have some sort of theta and we need some sort of tension. We want to know how many newtons are in that second cable. Are we okay with the picture so far? So we're trying to find a force. So forces, good place to start. Newton's second law. The net force acting on an object is equal to the mass of the object times its acceleration. Well, I assume we can figure out what the acceleration needs to be.
1 million miles an hour.
I certainly hope a chandelier hanging from the ceiling remains hanging from the ceiling and doesn't fall. Kind of the point of hanging it up. So what's the acceleration? 0. Call this an equilibrium problem. Acceleration 0. It's not going to speed up or slow down or change direction. It's just hanging there. So to approach any force problem, number 1, you want to draw the free body diagram. So draw the forces acting on the object you're interested in. We're interested in the chandelier. It's the object that's hanging. It has a force of tension from this cable. We'll call it force of tension 1. And it has a force of tension from this cable. Call it force of tension 2. Is that all? Gravity. We can't get rid of gravity. So the force of gravity is pulling downwards. What Newton's second law is telling us is since the acceleration needs to be 0, the net force acting on the chandelier must be 0. Whatever force is pulling to the right has to be balanced out by the same force pulling to the left. Whatever forces are pulling up have to balance out with the force pulling down. If they don't balance, if the net force is not 0, then there will be an acceleration. And that chandelier will start moving, which we don't want it to do. Now remember, vectors, we can only add x components together, so we'll only add the forces in the x direction. Those will equal the mass of our chandelier times the acceleration in the x direction, which is 0. Then we need to sum up the forces in the y direction as well. Those will equal the mass times the acceleration of the chandelier in the y direction, which is also 0. But we need to separate the forces into their x components and their y components. We can only add the x components together, and we can only add the y components together. So let's do the x components first. Force of tension 1. It has an x component and a y component. The x component and the y component meet at a right angle. Just vectors. We know vectors. We've been using vectors all along. What will the x component of force of tension 1 be? Our angle 20 degrees is right here. Force of tension is 300 newtons. So this x component will be 300 newtons times the cosine of 20. It'll be negative because it's pulling to the left. So we have negative 300 newtons times the cosine of 20 degrees as the x component of force of tension 1. Force of tension 2 also has an x component and a y component. Meet at a right angle. The x component I'm going to call it force of tension 2x. We don't know what it is. We don't know the force of tension, nor do we know the angle. We know it'll be force of tension 2 times the cosine of whatever that angle happens to be. But that's the same thing as saying force of tension 2x. You okay with that? What about gravity? What's its x component? 0. It's not pulling to the right or to the left. So plus 0, I'm not going to bother to write, but you're welcome to if you want. So these are the forces acting in the x direction. So those have to add up to equal mass times acceleration in the x direction, but that happens to be 0. So those forces have to add up to be 0. So it won't accelerate in the x direction. What that means is the force of tension 2, the x component, is equal to 300 newtons times the cosine of 20 degrees. So 282? Is that good enough? Thank you. Okay. So we know one piece. We need to know another piece in order to figure out the overall force of tension in cable 2 and the angle. But we haven't summed up the forces in the y direction yet. So let's do the y direction next. Force of tension 1 has a y component. The y component is pointing upwards. It's 300 newtons times the sine of 20 degrees. You okay with that? Force of tension 2 has a y component as well. I'm going to call it force of tension 2y. Now please, the common mistake is to think the y component of force of tension 2 is the same as the y component of force of tension 1. And that's because the actual y distance in meters for both cables is the same. That vertical distance is the same, but that does not make the vertical forces the same. So we need to leave this as force of tension 2y so we can figure out what it is. It's not the same as the force of tension 1y. Okay?
Question.
Yes?
Can't you just take the force of tension 1y and subtract the force of gravity?
That's what we're in effect going to do.
Sorry.
Let's get there. So we have force of tension 1 component pulling up, force of tension 2 component pulling up, then we have the force of gravity pulling down. So we're going to put minus, what determines the force of gravity? mg, mass, acceleration of gravity. So minus mg. Those are all the forces in the y direction. So those have to equal 0 since there's no acceleration in the y direction. We know m. The mass is 40 kilograms, given in the problem. We know g, 9.8 meters per second squared. So the force of tension to y component will equal, bringing the other stuff to the other side, mg, so 40 kilograms times 9.8 meters per second squared, minus the 300 newtons sine of 20. So plug that in for me. 280 what?
280.
Do we have agreement? Fabulous. Thank you. So force of tension 2. Let me move my force of tension 2 label. The x x component we found to be 282 newtons. The y component we just found to be 289 newtons. So we certainly can find the hypotenuse, which will be the overall tension in the cable. So 282 squared plus 289 squared, square rooted. Sorry,
I'll let somebody else.
I didn't hear what you said, so 403.8, so 404? 404 newtons. So the force of tension 2 is 404 newtons. The angle it makes with the ceiling. This angle up here is the same as this angle down here. So inverse tangent of 289 over 282, it's going to be awfully close to 45. 46? 46 degrees. Now we don't have to add 180 to it. We don't have to say north, south, or east, or west. The problem specifically asks what angle does it make with the ceiling? It makes a 46-degree angle with the ceiling. That's all we need to know. Questions? So we summed up the forces in the x direction, set it equal to 0 because the acceleration in the x direction is 0. We summed up the forces in the y direction. We made the ones pulling upwards positive, the one pulling downwards we made negative. Set those equal to 0 because the acceleration in the y direction was 0 as well. That allowed us to find the x and y components of that tension 2.